Before GPT-4 could answer a single question, it made about 100 trillion mistakes. That is not an exaggeration. And the process it used to go from 100 trillion mistakes to the most capable language model in history. That process is something most developers have never seen explained clearly. Today, we fix that. You are probably already using AI every day. GitHub Copilot finishing your code. Claude helping you debug. ChatGPT drafting your documentation. But here is the uncomfortable truth. Most developers using these tools have no idea how they actually work. And that gap matters. When an AI model gives you wrong code, do you know why? When a model hallucinates a function that does not exist, do you understand what went wrong? When you choose between GPT-4 and a smaller local model, do you know what that trade-off actually means? Understanding how AI learns does not just satisfy curiosity. It makes you a better developer. It helps you use these tools with precision instead of hope. So let us get into it. Here is what we are covering today. First, what does it actually mean for a machine to learn? Not the marketing version, the real version. Second, the training loop. This is the engine behind every AI model ever built. If you understand this, you understand 80% of what is happening inside any model you use. Third, the loss function, the mathematical concept that tells a model how wrong it is. Fourth, gradient descent, the algorithm that makes a model less wrong, one small step at a time. And finally, what all of this means for you as a developer working with AI in 2026. No PhD required. Let us go. Let us start with the most misunderstood part of AI. When we say a machine learns, we do not mean it reads a textbook and memorizes facts. The traditional approach to AI, the one that failed repeatedly through the AI winters, was to program rules manually. If the user says X, respond with Y. If the image contains this pattern, classify it as a dog. That approach has a ceiling. The real world is too messy for handwritten rules. Machine learning does something fundamentally different. Instead of programming rules, you feed the machine data, millions or billions of examples, and you let it find the patterns itself. Think about teaching a child to recognize dogs. You do not give them a rule sheet listing 4 legs, fur, tail, barks, floppy ears. You just show them thousands of dogs. And eventually, they recognize dogs they have never seen before. Machine learning works the same way. You show the model data. The model makes guesses. You tell it how wrong those guesses are, and it adjusts. That is learning, not rules. Adjustment. This brings us to the most important concept in all of machine learning, the training loop. It has 4 steps, and every AI model you have ever used went through this loop billions of times before it was deployed. Step 1, the forward pass. You take a piece of training data, an image, a sentence, a number, and you feed it into the model. The model makes a prediction. Before training, this prediction is essentially random. The model has no idea what it is doing yet. Step 2, calculate the error. You compare the model's prediction against the correct answer. The gap between what the model predicted and what the correct answer was, that is the error, also called the loss. Step 3, the backward pass. This is where the magic happens. The model looks at that error and figures out which parts of itself caused this mistake, which internal settings were most responsible for being wrong. Step 4, adjust. The model updates its internal settings, called weights or parameters, to reduce the error. Not by much, just a tiny nudge in the right direction. Then you repeat, millions of times, on millions of examples. Forward, error, backward, adjust, repeat. At the beginning, the model is completely lost. But with each iteration, each pass through this loop, it gets slightly less wrong. And with enough data and enough loops, it gets very good. Let us talk about the error measurement more precisely. In machine learning, this is called the loss function. The loss function is the mathematical formula that measures how wrong the model is. For a simple image classifier, the loss measures, I said this was a cat. The correct answer was a dog. How far off was I? For a language model like GPT, the loss function measures something different. I predicted the next word would be code. The actual next word was algorithm. How surprised should I be by that? Here is the key insight. The goal of training is not to get the right answer. The goal of training is to minimize the loss. These sound like the same thing, but they are not. When you minimize the loss, you are teaching the model to make predictions that are consistently close to correct across an enormous variety of inputs, not just memorize the training data. The loss function is your compass. It tells you how far you are from where you want to be. Without a well-designed loss function, the model does not know what it is optimizing for. And models are very literal. They will optimize for exactly what you measure and nothing else. Now for the algorithm that makes all of this work. Gradient descent. Imagine you are standing on a mountain in complete darkness. You cannot see anything. Your only goal is to reach the lowest point in the valley. What do? You feel the ground around your feet. You find which direction slopes downward. You take one small step in that direction. Then you do it again. Step by step, you descend toward the valley. Gradient descent is exactly this, but for mathematics. The model is standing on a mathematical landscape where altitude represents loss. How wrong the model is. The goal is to reach the lowest point, minimum loss. The gradient is the slope. It tells the model, this direction makes you more wrong. This direction makes you less wrong. The model takes a tiny step in the direction of less wrong, then recalculates, then steps again. The size of each step is called the learning rate. Take steps that are too large, and you jump over the valley. Take steps that are too small, and it takes forever to get anywhere. This is why training powerful AI models takes weeks on thousands of GPUs. You are running gradient descent on trillions of parameters across billions of examples. GPT-4 has an estimated 1.8 trillion parameters. Each one is a tiny adjustable setting inside the model. Each one was nudged by gradient descent again and again, until the model as a whole became capable of reasoning, writing, and coding at a level that surprised even its creators. Let us talk about scale, because this changes everything. A small model, a spam classifier, might have a few thousand parameters. It learns patterns from a few thousand emails. A medium model, a sentiment analysis tool, a recommendation system, might have a few million parameters. GPT-3 has 175 billion parameters. At that scale, something unexpected happened. Models began demonstrating capabilities that nobody programmed into them. They could write poetry, solve logic puzzles, translate between languages they were not explicitly trained on. This is called emergent behavior. It is still not fully understood. But here is what we do know. The core mechanism never changed. Forward pass, loss, backward pass, adjust, repeat. The same training loop that works for a spam classifier works for the most advanced language model in the world. The difference is scale. More data, more parameters, more compute, and the same four-step loop running for months on end. So why does this matter to you as a developer? Because when you understand the training loop, you understand the limitations. A model can only learn what is in its training data. If the data is biased, the model will be biased. If the data does not contain certain knowledge, the model cannot know it. When a model hallucinates, confidently states something false, it is not lying. It is doing exactly what gradient descent trained it to do, predict the most likely next output given the context. It just happens to be wrong. When your coding tool suggests a function that does not exist, it is not confused. It is generating the most statistically likely response based on patterns in its training data. The pattern matched. The function just never existed. Understanding this does not make AI less useful. It makes you better at using it. You know when to trust the output. You know what kinds of prompts produce better results. You know why providing context improves accuracy, because you are shifting the statistical landscape the model is navigating. The developers who understand how AI learns are not just users. They are engineers who know the tool they are working with. That is the simple truth behind machine learning. Not black magic, not mysterious intelligence. Just a training loop, forward, error, backward, adjust, running at a scale that produces something that feels like thought. For more content, please like and subscribe.